if I wanted to look not only if 3 of my patients were to go into remission, but I wanted at least 3, or greater or equal to 3, meaning that perhaps I wanted the probability that X was greater or equal to 3, meaning that it could be 3 or it could be 4 of my patients were to go into remission. Again, this is on page 192 with a different application, but the exact same mathematics. So I've already figured out the probability of exactly 3 would be 0.0036. And now I want to add to that probability the probability that 4. I choose, how many different ways can I choose 4 of my patients out of 4? There's one way. Everybody gets chosen. That's the only option. Well, if you do a combination for that, it's 4 factorial over 4 factorial over 4 minus 4 factorial. If you simplify that down, it's just 4 fact over 4 fact times 0 fact. This, we know 0 fact from earlier is 1, so we have 4 fact over 4 fact, which is equals 1. Okay, there's one way to choose all 4 people, and that's by choosing everyone. Now, the probability of success is still 0.1. That happens. 4 people all get success. The probability of failure is 0.9. That's given by 4 minus 4, or 0 people fail. Okay? Simplified out, 1 times 0.1 times 0.1 times 0.1 times 0.1 equals 0.0001. I add that to my probability, 0.006, and the probability that 3 or more of my patients experience remission is 0.003, or 0.37%, or less than 1% chance. Again, in example 5.3 on page 192, we start and we look at the probability that X is less than 3, or the probability that less than 3 of my patients go into remission. Okay? That's not defining if it's 2, 1, or 0. I'm asking the probability that less than 3. Okay? So if I have 2 patients experience remission, although that's wonderful, it is less than 3, or 1 patient is less, or 0. Okay? It doesn't distinguish which 0 patients go into remission, 1 or 2. It doesn't distinguish. It's just asking that it's less than 3. What's the probability that happens? Well, I didn't have the board space to write this all out, but if you follow along, you can see if we just do this, repeat the binomial exactly as it was, we have 0.6561, or 65% chance, 65.6% chance that 0 of my patients go into remission. There's a 29% chance that only 1 of my patients goes into remission. And there's a 4% chance, or 0.0486. There's a 4% chance that 2 of my patients go into remission. So how we figure out probability X is less than 3? Well, we look at the probability of those observations that are less than 3, 0, 1, and 2. We add them up and we get 0.9963, or 99.63% chance that less than 3 of my patients go into remission. So this would be written, again, 99.63%. Well, you notice here, we figured out the probability that X is 3 or 4, greater than 3. So we could have just taken 1 minus the probability that X is greater or equal to 3. We could have taken that. And that ended up a little messy. But we could have done the 1 minus the probability X is greater or equal to 3, and we'd end up with the same 99.63%. The mean and standard deviation of the binomial are given on page 194. It's very simple. The mean given by mu, again Greek letter mu, M or U, mu. Mu is N times P. N times P, that's it. The number of people in our sample times the probability of success. So in our cancer study, we had 4 patients. We had the probability of success of 0.1. We have 0.4. The expected number of successes we have is 0.4. Now remember, this is a discrete distribution, so we can't have 0.4. We cannot have 0.4 humans or 0.4 people experiencing remission. So we would have to round that down. Yeah. In our case, if we're dealing with people, we would round that down, and so we would say that the expected value is that nobody experiences remission. Okay. Standard deviation is almost just as easy. It's N times P times 1 minus P, all under the square root. N, number of people in my sample, probability of success times the probability of failure, all under the square root. In ours, it's 4 times 0.1 times 0.9. Take the square root. In our standard deviation is 0.6. Okay? You could also write that as the binomial 0.4, 0.6. With a mean of, should label this mu equals 0.4, sigma equals 0.6. Okay? Your homework for this section is 5.23 and 5.24 in the practice for binomials. The Poisson distribution is the second discrete probability distribution we're going to look at. And the Poisson distribution is generally given in a problem dealing with time or time intervals. So this has wide applications in business if you're looking at the number of people visiting a kiosk, a banking teller, an ATM in a given amount of time. Okay? I want to introduce you to some new symbols. We have lambda, the Greek letter lambda. Okay? Lambda here, also lambda here. Lambda is given the expected number of events. For instance, you expect to have 3 people per minute come to an ATM over the lunch hour. Okay? You expect 100 people per hour to come to McDonald's over the lunch hour for 1 teller. Whatever. The expected number of events, E, equals 2.71828, 1828. So 2.71828, that's E. That's Euler's number. It again is often used in mathematics. And X is the number of events. Okay? Here is our formula. Again, the probability of X is e to the negative lambda times lambda to the x over x factorial. Now, a bit intimidating. We're going to break that down in just a second. Before I do, I want to... the expected number of events is lambda. Lambda also is the variance, and the square root of lambda is the standard deviation. So, this is pretty nice about the distribution, is that the expected number of events, or the expected value, the variance, are the same. They're both lambda. If we wanted to answer the question, what is the probability that in a minute exactly 2 customers arrive, given we expect that 3 customers should arrive per minute? Okay, this is on page 198. What is the probability that exactly 3 customers arrive at our kiosk, given we expect 3 to arrive in a minute? So exactly 2 would be less than what we expected. Now, lambda is equal to 3. Again, e to the negative lambda, lambda to x, x factorial. We can plug in. We know the probability that x is equal to exactly 2 is e to the negative lambda, which is 3. E to the negative 3 times lambda, which is 3, raised to the x, which is 2. We're looking for 2 customers, over 2 factorial. Again, we're looking for exactly 2. We expect 3. And So we have our Poisson distribution. If you simplify this, 3 squared is 9. E to the negative 3, that negative exponent will drop Euler's number down into the bottom of our equation. So we have 2.71828. This should be squared. Oh no, I'm right. Let me back up. That's right. To the 3. 2 times 7, 1828. Raised to the 3. Now that's a positive 3 because when you drop a negative exponent into the denominator, the negative sign disappears. Times 2 factorial. 2 factorial is 2 times 1, which is just 2. Simplifies to 0.2240, or 22% chance that we have exactly 3 customers come to our kiosk, given that we expect 3. Now,